Okay, so I'll tell you about RISC-V. Instruction sets want to be free. Now you're all, hardcore systems people here. So I want to ask you a couple of rhetorical questions, which is, why do instruction sets matter at all? Like, why do you really care about these? So here's a few questions. Why can't Intel sell mobile chips? Because they have the wrong instruction set, right? All the mobiles are based on ARM, v7, v8, ISA, right? Vast majority of them. Even when Intel staples dollar bills to those chips, they cannot sell them into that market, right? They're effectively useless because they have the wrong ISA. It's not a rosy for ARM because why can't ARM sell servers? Or more exactly, why can't ARM partners sell servers? Well, the reason is they run the wrong instruction set. Almost all laptops, desktop servers are based on the AMD 64 architecture. Most of those are built and sold by Intel. So why is Intel selling an AMD-designed ISA? Well, ISAs are so important that back when they're making the transition from 32-bit to 64-bit, Intel tried to get rid of their second source by trying to foist something called Itanium onto the market. How many of you use the Itanium system? How many of you like the Itanium system? Exactly, right. So that was a monopoly play by Intel that thankfully failed. AMD figured out how to do the obvious 64-bit extension and keep compatibility with 32-bit, and now Intel is forced to go make those same servers. How can IBM still sell mainframes? Right, so the IBM 360 ISA, this is the oldest surviving ISA. It's like over 50 years now. And the reason is because of software, right? You develop all this software for a given instruction set. It's really hard to move it to a different one. So, the ISA is really the most important interface in a computer system because it's where hardware meets software, right? Now, one other thing you'll notice about this is so important that basically instruction sets are what segment our industry, right? It's really divided along ISA lines. Okay. Now, what's surprising is most other parts of the industry, we have open standards. We have things like Ethernet for networking. Some of you may remember the bad old days when there was DECnet, Token Ring, hundreds and hundreds of other proprietary network standards. Right now, if it's not Ethernet, it's basically dead. Notice, though, that the big vendors are trying to push proprietary network standards in the data center, things like OmniPath, etc., right? But basically, Ethernet is an open standard. You can have open implementations of it. You can have proprietary implementations of it. It's a free and open standard, relatively. And most of the way down the stack, you have things like POSIX for the Unix API. C languages, that's a standard. You can have GCC or you can have proprietary compiler, and so on down the stack. Graphics, OpenGL is a standard. You can have free and open implementations or closed source implementations of that. But down at the instruction set level, it's proprietary. Your choices right now are basically x86 or ARM, and even those aren't really choices. And because there is no open standard, you cannot have an open implementation of the ISA. Intel will sue you if you try and make an x86. ARM will sue you if you try and make an ARM without having a license from them. Okay? Nobody's trying to make 360s anymore. So why are these things proprietary? They're so important, yet this standard is proprietary. Now, the reason isn't, I'll just give you a hint, the reason is not because Intel and ARM are fantastic designs that are so superlative that there's no reason to do anything better, right? That's not the reason. They're pretty dismal ISA designs, yet these are entrenched as the industry standard. Now, just to complicate things a bit more, this might be interesting to some of you folks who haven't looked inside, but in a system on a chip these days, there are many, many different ISAs. x86 and ARM might be the ones that you see, but if you look inside a modern SoC, you'll find, as well as that applications processor, which is usually on ARM these days, you'll find graphics processors, image processors, radio DSPs, audio DSPs, security processors, power management processors, lots and lots of little processors on that die. And it's not unusual to have 15, 16, 20 different instruction sets on one chip these days in all these different cores. So, why are there so many? And why don't they all just use the same ISA as the apps processor? Well, one reason is that apps processor was designed just as an apps processor, and it doesn't scale down to serve these other functions. Another reason is that these pieces are bought from different companies, each of which have their own proprietary ISA that they're supporting, right? And in a lot of cases, the companies developing these chips, their engineers will decide, we can just build a simple RISC core over in this corner to do this function. We'll just port GCC, that's all we need to do. They then regret that when the product's successful because they have to keep supporting it. And they really don't have the resources to do that, right? Oops. This is a real pain for the industry. There's like many ISAs on a single chip, each of which has a unique software stack, right? Now imagine you have like 15 different ISAs and none of them run the same version of GCC, right? You're trying to write code for your standard library for example. So this is a major pain. So why do we really need all these different ISAs? And do they have to be proprietary, right? So the RISC-V project, the premise is, what if there was just one free and open ISA that everybody could use for everything? Pretty simple idea. So that's what we've been doing in RISC-V. So I go back to the origins of RISC-V. So my group, over the many years, have built lots of architecture research chips. And every so often, you get to this point where you start a new round of research and you want to pick the ISA you're going to use as the basis for your systems for the next bunch of projects. And the considerations are usually, what has the most software available that you can just reuse in your project. Back then, as in now, the obvious choices were x86 and ARM, right? Those are the two popular ISAs. They still are now. But we started looking into these, and every so often I get, I'm a computer architect, I like building chips, I like building processors. I get this, crazy idea that maybe I'll go build an x86, right? And as soon as I do, I'll crack open the instruction set manual. And what's the first opcode? AAA, right? They're listed alphabetically, so you see AAA. And what is that instruction? Anybody know? Yep. ASCII adjust after addition. This is a fine instruction. It must be important. It's right up there at the front, right? So what does this instruction do? Do you know?
I believe it's a fix-up when you do math.
Right. So it has one register, source and destination, AL, implicit register. If the low nibble is greater than 9 decimal, or the auxiliary carry flag is set, then you add 6 to the low nibble, discard the overflow, increment the high byte of AL, and set the carry flag and auxiliary flag. Else, clear the flags, right? This is obviously a really important instruction. And you can tell it's important. Not only is it right at the front of the opcode manual, it also has a single byte encoding. And you're obviously going to use this so much you want to save code space, right? So single byte encoding, ASCII, I couldn't make this up, right? I had to look this up, right? So this is the part of the industry standard instruction set that connects software to hardware, right? Now, ARM is a RISC design. You can tell it's a RISC design because there's an R in the middle of the name that stands for RISC, right? These folks are actually very inspired by my colleague Dave Patterson's work on RISC back in the early 80s. They read all those papers. Like Dave likes to say, he'd give these guys a D for what they did with that. So here's an ARM RISC instruction. The opcode is LDMIAEQ, okay? So what does that instruction do? It's written out there. What it does is it's a load multiple increment address. So it writes to 7 registers from 6 loads. It only executes if the equal condition is set. And by the way, one of the registers it writes is the PC, so it's actually a conditional branch as well. And on the ARM, the addresses you branch to can change the instruction set you're using. Okay. So this is a RISC instruction in name only, right? So ARM is better, but it's not really that much better if you actually look at the details. So these are the 2 industry standard ISAs. This is what people are living with in terms of, it may be invisible to the software folks, but the hardware folks, this is the complexity they're dealing with implementing this stuff, right? Okay, so, this instruction actually isn't that uncommon. A variant of this is how you do a return from a function call. You basically read back the registers, and in the process, you write the return address in the PC, and it returns. Okay. Anyway, so get back to RISC-V. So we looked at this, and we're like, we could use ARM. It's a bit easier than x86, but it's still a mess. We don't really want to do that. And also, the IP issues made it impossible. So, at university, I like to build chips. I like to design stuff. I like to share it with my colleagues at other universities or elsewhere. Here's the RTL. We designed a processor. Why don't you go use it? Can't do that x86, and you can't do that with ARM either. Paraphrased like Adams, I figure ARM as being mostly impossible. And also back at that time in 2010, there was no 64-bit version of ARM. This was pre-ARM v8 coming out. Okay, so we decided we'll do our own clean slate ISA. We're tired of hacking up on these industry ISAs. So clean slate ISA just for ourselves, for research, for teaching. Make it very simple. So The principal designers, I give them a shout out, Andrew Waterman, Yunsub Lee with the grad students, and then Dave Patterson and myself, we worked on this, the principal designers. So this is going to be a 3-month project in the summer, 2010. We'll just knock out a simple ISA. 4 years later, we published the frozen base spec. Now, the thing to realize is we didn't just sit in the room, pontificate about ISA design for 4 years. We actually spent a lot of time building chips. I think it'd been about 12, 13 chips based on versions of RISC-V ISA come down to Berkeley, ported compilers, operating systems, and iterated a lot. So this is, during this 4 years, we did a lot of iterations. And so we're pretty happy with this thing. It was going along quite nicely. Then we had this strange phenomenon of getting random emails from Indian engineers asking us, why did you change the spec? And we'd be like, who are you? And why do you care what we're doing here at Berkeley? And what had been happening was, for class projects, we'd often change the spec to do a problem assignment. Like, what if the ISA was like this? How would it change the pipeline? And some poor Indian engineer had been told by his manager to go use this thing, and we've been changing the spec on it, right? So at that point, we kind of realized something was going on. There was a pull from outside to use this thing. And so in 2014, we made a more concerted effort to push this out there to the community at Hot Chips in August 2014. And the response was really amazing. A lot of people kind of came up to us and said, yeah, we've been waiting for something like this. There is a really big demand there. And so that's kind of how RISC-V really got started. So one thing I'll sort of clear up, why is the name RISC-V? And it's pronounced RISC-V. And the reason is it's the 5th iteration of the RISC ISAs from Berkeley. So Dave always regrets that he dropped the RISC brand name from his later RISC project, so we reinstituted those. So this is RISC-1 and RISC-2. Notice these are called RISC-1 and RISC-2, not RISC-I and RISC-II. So it's not RISC-V, it's RISC-V, okay? Now SOAR was the next one, which is Dave Unger's project to put Smalltalk on a RISC, and we posthumously renamed that RISC-3. SPUR, some of you may know, that was the big project, multiprocessor project here, symbolic processing using RISC. We renamed that one RISC-4, and so this is RISC-V. And that's the first tape out we did of a RISC-V chip back in 2011, 28 nanometer FDSOI. Okay, so that's why it's RISC-V. Now we designed this ISA to be a universal ISA, so we wanted this to be good for everything. And what does that mean? Well, the most important thing is it actually can run existing software. So a lot of academics have these wonderful ideas for a new computer architecture, which seem really great until you realize you cannot build a C compiler for it, right? And then it's like, well, that's not very useful. So something that runs existing software stacks and languages well. And it was important to us, this is a native hardware ISA, not a virtual machine. Some people ask us, why did you do a new ISA? You could have just done a virtual machine that you could port to existing systems. That really is kicking the can down the road. Somebody has to then go build that hardware. And as you'll see, a lot of complexity is in mapping a virtual machine to a given hardware native ISA efficiently. People spend many 100 engineer years getting that to work well. You haven't really solved the problem. You want to actually decide what is in native hardware ISA, not just the virtual machine layer. Now, the virtual machine layer is an important thing to have, but that's a different problem at a layer up. We're solving the problem of what should the hardware do, right? We wanted to scale from the tiniest microcontroller up to the largest supercomputer. And this was actually strategic. We wanted to make sure that whenever somebody ported software or libraries to RISC-V at any one of these points, it would be reusable across the other points. So it wasn't just grand ambitions to have this scale, it was also to maximize software reuse across this whole space. And also across all implementation technologies, whether it's a softcore on FPGA or a custom design ASIC or a full custom design or future devices. And we want to avoid a lot of industry ISAs. The architects get enamored with, oh, we're at this point in computing history, this is the kind of machines that we built from this point forward. And they design the ISAs, so it's very difficult to scale them down to tiny implementations or scale them up to way more complicated ones. You want it to be good for microcoded, in order, decoupled, out of order. Another reason for this is I wanted to teach classes where I explained all these different styles. So having an ISA that didn't favor one of them was important. Another big thing, what we're actually doing research about was specialization. So, common theme with the end of Moore's law scaling, there's a lot more hardware, specialized hardware being designed all across the industry. And so we wanted this to be a good base to add your own custom extensions to build accelerators. Finally, one really big thing we focus on in RISC-V is stability. So given that this is free and open, we don't have an economic incentive to sell you version 8.1, 8.2, 8.3. We want something that's stable, that you can build on, that's not going to change. So when we released the user ISA, we froze it and said, this is it. It's not going to change. You can put this stuff, embed the processor in concrete. In 50 years' time, you should still be able to find the tool chain for it. Right? And we viewed that as very important as well. Excuse me. So we weren't the first people to think about doing a free and open ISA. So a couple of other ones deserve mention. So Sun, to their credit, came out with Spark v8, made that an IEEE standard. And both Sun and a company in Europe, Geisler, funded by the ESA, European Space Agency, they offered open source cores. Unfortunately with Spark, it ended up getting bought by Oracle, and that's kind of now disappeared off into Larry Land or whatever, so that's owned by Oracle. Also, it wasn't the best ISA. We ribbed Dave all the time. He was heavily involved in Spark's definition. And every project I've ever used Spark in, the register windows have been a major pain, either in the hardware or in the software. So we didn't want register windows. Open RISC was an interesting project. This was a bunch of Slovenian undergraduates who took the DLX design from Dave and John Hennessy's computer architecture book and basically typed it into Verilog and made that available. We looked at that when we started this project, and it had some traction, but it kind of fizzled out, and it wasn't a lot of technical failings in the design, and they hadn't really separated architecture from implementation. So we didn't really like that design, so we decided to do our own thing. But that was something along the same lines. And another thing, I think, with both these projects, they started in the microprocessor era, when you're competing with processors, you're basically competing with microprocessors. Here's a complete chip that's just a microprocessor, from Intel or somebody else, and you come along with an open source thing, well, how's that going to compete? What's different now is most chips are SoCs, but the processors are soft that you're synthesizing. And in that space, open cores have a much bigger part to play, right? So I think it's a question of timing here as well. So what's different about RISC-V? Well, it's really simple. It took us a long time to make it this simple, but it's far smaller than the other commercial ISAs. It's a clean slate design. Lots of separation. It's very modular. So the user and the privileged ISA designed to be completely independent. And we avoid baking in assumptions about microarchitecture or technology. It's modular. So it's designed with a very small standard ISA and then multiple extensions. It's designed for extensibility and specialization. So one place where it breaks with the original RISC canon is it has variable length instruction encoding as well. And we use that for compression. And that also gives us a vast opcode space for extensions. And the idea is to be stable, like I mentioned. So the base and standard extensions are frozen. When we make additions, it's via optional extensions rather than a mandatory bump in the version that everybody has to follow, right? Okay, so just to quickly go over what is it. I don't want to spend too long here. It's a lot of details. There's 4 base integer ISAs, 32-bit, 64-bit, 128-bit address space. So when we started the project, we put the 128-bit address space version in there, kind of as a joke, because the only thing that really kills an ISA is running out of address bits, right? But after talking to a bunch of large-scale cloud providers, they're very interested in 128 bits because if you look at what's happening in the data center, a lot of non-volatile memory is going in. People are putting in multi-petabyte NVM arrays, and they're putting in faster networks. They would like to access those large arrays more quickly than over a network. And so there is interest in that 128-bit address space because people see over the next decade, we're going to run out of address bits if you actually want to address many, many petabytes of non-volatile memory over a very fast network. All right, so it's less of a joke than we thought it was, but it's in there and it turned out to be easy to support in the RISC-V family. So you lead, for the integer base, there's less than 50 hardware instructions needed. And those hardware instructions give you a modern software stack. So with those 50 instructions, you can build GCC, you can have dynamic linking, position-independent code, you can run an OS, everything, just with those base instructions, right? So it's designed for the integer base, very, very simple. And this is a great boon for teaching. I can teach a whole class with all the tools and bring up the whole data path in one lecture, right? This is great. Then there's the standard extensions that give you other operations you'll need. And the base is a very standard RISC encoding, 32-bit fixed width. And as I said, all those have been frozen, right? So this is just the encoding. For those people looking at encoding, we designed the encoding. It took a lot of work to make it this simple. People who've been doing implementations appreciate how much time we spent into making it this simple in terms of all the registers are in the same place in every instruction format. The immediates are always sign extended from the same bit in the register, which helps with circuit complexity. And the way we scramble the immediates, if you look at the spec, you may wonder why the immediate's so funny looking. It's to simplify the hardware again. And so people doing the low-cost implementations really benefit from these little tweaks you made. So quickly, a few things that might be interesting to the OS community. So the atomic operations extension. Atomic ops has two classes. We have AMOs, so fetch and op, of various kinds, as well as load reserve store conditional. And the load reserve store conditional has a forward progress guarantee for short sequences there as well. Now one thing that we are, one thing is that all these AMOs can be annotated a couple of bits to implement release consistency or sequential consistency. Those are familiar with ARMv8, they came out with the same kind of thing a bit later. We had this in the earlier version of the spec. One thing we are working through is some issues in the memory model that are non-trivial. And I think just like every other ISA, there's a bunch of memory model issues to resolve. And so we're working through that right now. Those are tough problems and they take a while to figure out. So the variable length encoding, so that the base ISA is designed that branches and jumps go to any 16-bit boundary. So the only real penalty, even though the base ISA is all 32 bits, fixed width, naturally aligned on 32 bits, all those 32-bit instructions have the bottom 2 bits being 1-1. If they're not 1-1, then it's a 16-bit instruction. The reason we did this was to support adding a compressed extension. So compressed instructions are 16 bits. And compressed code is really important in two scenarios. One is, in embedded, it's important to save static code size. So, the cost of flash in embedded devices is critical parameter. You want a smaller code as possible, but also high-end commercial workloads. In servers, what you'll find is a lot of the execution time is dominated by I-cache misses. Instruction working sets are very large in commercial workloads. So cutting that down with compression is very important too. So this compressed section just mixes in with the regular instructions. And we kept a very simple model. One compressed instruction expands to one regular instruction in the base ISA. And it's tiny. It's like a few hundred gates to build one of these decoders. And getting this, we get about 25 to 30% smaller code size. So just to give you a comparison, this is just across just as a working set, spec-in code size. And on 32-bit address space, we're comparable to the ARM thumb ISA, which is one of the densest ISAs out there. In 64-bit space, though, we're far denser than anybody else because ARM, when they did V8, didn't put in the compression. All right, so it can significantly smaller than any of the other 64-bit address space ISAs. Okay, I'm just going to skip through this. We're working on a vector extension. It'll give us better performance for SIMD kind of operations. This is a work in progress. Now, the privileged architecture. So this is an OS community, so I thought I'd spend a little bit of time here. So RISC-V's privileged architecture, there are 4 basic privilege modes. One thing to say before I start all this, RISC-V was designed so the user architecture and the privileged architecture are completely separate. So you can redesign the whole privileged architecture if you see fit. And this is meant to be just a reference, boring one that runs existing software, right? There's a lot of people out there with interesting ideas for completely new different ways of organizing the privileged architecture. But this is meant to run conventional Unix-like OS as well, right? There's 4 modes: user mode, supervisor mode, hypervisor mode, machine mode. And basically you can support 1, 2, 3, or 4 of these. The machine mode is the only mandatory one. So in a simple embedded system, you just have machine mode. Everything is basically bare metal. All code is inherently trusted because it can touch anything. And there's only a few bits of extra machine mode state you need to provide machine mode. This is very simple. Low-end microcontrollers will be like this. We actually support what we call machine mode and user mode. And this is for embedded systems that need some security. And the idea here is machine mode is a secure mode. User mode is locked off from physical addresses by a memory protection unit and can't touch everything. But one thing we do provide in RISC-V is interrupts can be delegated to user mode directly. So if you have something that you would consider being a standard embedded app that needs to respond to interrupts quickly, you can still have that, but have it be isolated off from secure parts of your system, because you can delegate interrupts to there. That device can touch the devices you let it touch directly without any OS intervention. So you can get a secure kernel running untrusted user mode stuff that is touching devices directly, the ones you let it touch. Right, so that's one of the RISC-V operating modes. For the supervisor mode, which is where Unix-like OSs run, we decided on 4K pages, and this was after intense debate with lots of people. So 4K pages are the basis of all the virtual memory schemes, basically because of fragmentation. If you're building, you need 4K pages. A lot of systems now, some architects would argue you need bigger pages to give you more TLB reach. We'd argue you just need a better TLB hierarchy, so you're not affected. Like basically, I think most architects have under-provisioned the TLB hierarchy in most processors, and you should just go make 4K pages work better instead of giving you 16K or 64K pages, which cause havoc with things like disk caches, right? So we believe you should support 4K pages, support them well. A conventional nested page table with super pages, so 2 mega pages and 1 giga pages are also supported in the architecture. So I think already our Linux port has the transparent promotion. I must admit ignorance whether BSD does the same thing. So one thing about our supervisor mode, it runs on top of machine mode, so that we don't trust the Unix OS with the system. So machine runs underneath. It will then load supervisor mode and start the OS running in S mode, and you can cordon off parts of the physical space from the supervisor. Again, this is for security and also for a lot of applications where you want to have side processes running that don't trust the OS, right? So the OS can be given, access to a portion of the machine. For those of you familiar with LPAR, it's kind of like LPAR. You have a logical partition on the physical address space, all right? That's kind of what we support too. In designing the whole thing, we wanted to have really clean virtualization stacks in the sense of the layers communicate through very distinct interfaces. So, applications talk through an API to an OS or whatever's below that. Supervisors don't talk to hardware, they talk to a supervisor binary interface. And similarly, hypervisors don't even talk to the hardware, they talk to a hypervisor binary interface. And so our goal here is to really hide differences between hardware implementations and also provide more security, more flexibility really for implementers. And the goal is really that a single distribution can run on any platform out there rather than having to compile it in some hardware-specific stuff. So the SBI is kind of a lot of things that might be done with registers or special instructions. We're trying to abstract into an SBI to give the hardware more flexibility in how it's done. And one thing, if you're really corrupted by how bad x86 is at taking system calls or context switches, those numbers, how long it takes that thing to do that, you shouldn't use that to worry about these context switches. These can be much faster than current x86 is, because we don't have all that baggage to implement this stuff, and we hope we can get a cleaner interface there out of these things. So I'm just going to wrap up on RISC-V instruction set. So it's very simple, and to show you how simple it is, you just put the whole thing on one slide. So Dave put this together. It's equivalent of an old IBM 360 green card. So here's the RISC-V instructions for the 32-bit version. Then we can add the privileged instructions, then the multiply divide extension, then the atomics, single double quad precision floating point, the compressed extension, then a few extra instructions to get added for the 64-bit address space, 128-bit address space version, and then we're pretty much done. And that's the whole ISA. And so, the joke is you can tell it's a RISC architecture because the manual doesn't need a staple, right? That's kind of, all right. So there you go. That's the RISC-V green card. And I can read these instructions because I'm standing right here. It's not that dense, right? So we kept it really simple. Okay, so I'll do a quick time check. If I can get through the 500 microphones I have on me. All right. Okay, a little bit of time. So far I've talked about the instruction set, and that's becoming a standard. But I'll talk a little about at Berkeley. Like I said, we did a lot of iteration on this, and what we did was build a family of a lot of hardware design. We actually encapsulated these as core generators. So for those interested in hardware design, we use a language called Chisel we developed at Berkeley, and Chisel is embedded in Scala. So it's a high-level programming language we use to write hardware, and it lets us be very productive, and we generate lots of chips. So we have in-order cores, out-of-order cores that we developed at Berkeley. This is a pretty complete in-order core. It's not a simple in-order core. It has full IEEE, floating point, MMU to support OSs. It has pretty extensive branch prediction. And just to give you a comparison, people are asking us, how do you compare against ARM? So pretty well, actually. So this is a comparison against the industry standard ARM core in the same process technology. We actually got the same libraries as these guys. So, unfortunately, in the embedded space, Drystone is the benchmark of choice. I'm not going to say anything more about that, but we do better on Drystone. Significantly smaller, significantly lower power, significantly faster. So that's just one design point. It's just a few grad students at Berkeley competing against ARM. So the out-of-order core, we developed an out-of-order core generator. And do the comparison against the A9. So ours is actually generated. We can build different cores. This is comparing a configuration similar to an ARM A9. And again, it's basically a lot smaller, a lot lower power, and faster. Now this isn't quite an apples and apples comparison. The A9 includes this Neon stuff, which is actually pretty big. On the other hand, Boom is 64-bit instead of 32-bit processor, and has a full fuse-mol add unit to support IEEE 2008, which the A9 doesn't have. So, you know, the whole point of this is to give you an idea that this ISA can lead to cores that are very competitive with the current industry cores, right? That's just some more numbers just showing how great we are. So at Berkeley, we built a lot of cores. We've taped out a bunch in 45 nanometer, 28 nanometer. You know, these cores run at, you know, over a gigahertz. And the energy consumption is actually very good. This is measured on silicon. There's a bunch more. We've actually done a 16 nanometer FinFET tape out here at Berkeley that didn't make it onto the slide. So this is an ongoing work, just a university group using this ISA to build pretty competitive chips. Okay, so now outside Berkeley, what's been happening? Well, one of the big things was a while ago, the Indian government decided to adopt RISC-V as the standard ISA of India. So we figured that's 1/6 of the planet down. We just got, you know, 5, 6 left to go. So why does India want to make RISC-V be a standard? Well, they had their own Indian microprocessor initiative running along, but it wasn't making much progress, and we just kind of overtook them, so they just hopped on board. The reason they're interested is two primary ones. One is semiconductors are very important in trade. If you don't have any indigenous semiconductor industry, your trade imbalance is just getting worse over time. So they need indigenous semiconductor industry. The second one is security. They just don't trust the IP from Intel or ARM or other places. They want control over the processors they build in their systems. So that's why RISC-V is very attractive to them. So they invested a lot of money, $90 million in one center, $45 million in another, to build RISC-V servers. So some of you may know the Low-RISC project based in Cambridge, UK. They've adopted RISC-V for this project to do an open source SoC, led by some of the people who did Raspberry Pi, and got frustrated by the fact that Raspberry Pi, the Broadcom chip used there, a lot of the stuff there is locked off and you cannot access, right? It's sort of hidden behind binary blobs. They want a SoC where you can actually get in and do everything with everything on the chip. So they've been using the Berkeley code base to develop this low-risk chip. One other big announcement, the last workshop, NVIDIA announced they selected RISC-V to use on all their future GPUs as the microcontrollers on there. So they did a comparison against their own homegrown thing, other industry commercial cores, and decided RISC-V was actually the best choice. And so now going forward, all NVIDIA GPUs are going to have RISC-V controllers on them. There's a lot of other companies developing RISC-V for use, and some commercial products already shipped. And you should see multiple commercial silicon implementations this year and next year. Probably this year for microcontrollers and next year for servers, server class chips coming out. So one thing that's amazing is the amount of activity, even though there isn't any commercial silicon yet. So after pushing this out, we had a lot of interest, and the industry guys thought we have to create something more long-lived to manage the standard. So back in August 2015, I incorporated this foundation. It's a nonprofit 501c6 trade association to basically standardize, protect, promote RISC-V. And in January of this year, we announced with the first 16 members, and by July, we're up to over 40 founding members. And it's pretty much, the goals of the foundation: make the standard open and license-free to everybody, always make the specs publicly available for download. The compatibility suite should always be available to anybody for download. The one way we protect the standard and prevent fragmentation is you can only use the RISC-V trademark for commercial products if you're a member of the foundation and you pass the compatibility suites, right? So just avoid people fragmenting. But a lot of companies have signed on, including a lot of the major companies like Google, IBM, Microsoft, Qualcomm, Western Digital, HPE. A lot of these guys, they're not just spectating, they're actually doing stuff, which is kind of amazing to me. So like I said, NVIDIA is going to be using it on future GPUs. HPE contributed UEFI ACPI to RISC-V project. I don't know if that's a good thing or a bad thing, but that was a lot of work. And it's not the kind of thing you do for fun. Google, the core bootloader, doesn't commit unless the RISC-V port commits. Right? It's a blocking port now at Google. So there's a lot of activity across the semiconductor industry in RISC-V. So if you want to learn more, the primary resource is the RISC-V.org website for the foundation. And all the proceedings from the first 4 workshops are up and available, the slides and videos. The next workshop is going to be right after Thanksgiving at Google in Mountain View, so please go sign up. I'll warn you that every other workshop is sold out, and we have to turn people away. So Google's pretty big, but it's not infinite size, so go sign up. This is the last workshop at MIT. over 260 attendees, 63 companies, 42 universities. So one thing is we've been looking at in the foundation is to do a roadmap for where RISC-V is going in terms of specifications. One reason to come talk to this community is, as BSD gets rolled into here. One good thing is BSD beat Linux into mainlining RISC-V, so thank you. Free BSD. Yeah, that's great. So basically what we're trying to do is step the privileged architecture. Every quarter have a new release of the privileged architecture, and hopefully in about a year's time, pretty much stabilize that. And partway through here, we're going to fix things in a way that we can change it, but they have to be upwards compatible. Because what you're going to see is, I think a bunch of vendors I know of are going to be doing some freezing their commercial implementations in the first part of this year, so we don't want to upset them too much. Also, we just need to get going on this. And so if you would like to get involved in this process of moving this forward, and kind of the goal is by the end of next year to have a complete stable platform in the sense of supporting Linux KVM or BSD Beehive, type 2 hypervisor, supervisor mode sorted out by that point in time, which means a lot of stuff has to happen before then. But that's kind of our pretty ambitious goal to get a platform spec. The goal is that a single distribution should run on any platform that obeys a spec. That's kind of the goal. Okay, so we're just going to wrap up here. So, why RISC-V? It's free and open. There's no proprietary lock-in. Anybody can build chips to the RISC-V standard. It's much simpler than others in terms of verification, security. That's very important. It's not going to change or disappear. If you may notice, other very important ISAs disappear over time. And why is that? If you look at a couple of big ones like VAX and Alpha, they disappeared when DEC went down. And if you built your software stack around those ISAs, you were kind of lost at sea. Even though you did nothing wrong, it was, DEC's management did something wrong. And you can do nothing about it because that ISA is owned by some IP holding company right now, probably. And you cannot resurrect it even if you wanted to, right? So, to me, it's kind of crazy that people built this whole world around ARM and x86 where it's owned by somebody else, right? And if something happens there and it goes away, like, for example, when ARM got bought by SoftBank, there was a sudden influx of interest in RISC-V. People kind of realized, yeah, it's like, hey, you know what? We need a plan B. This thing we relied upon isn't that solid and stable. The other thing is just, it's better than the commercial ISAs. Like people go through these phases of, oh, RISC-V is great, it's free and open. Then you look at it, and it's like, hey, you know what? This is actually pretty good. And then they can see they can use it in all these different places. So we're really seeing this very rapid uptake. So a pretty modest goal at this point is just become the industry standard ISA for everything. And we're kind of well on our way. So, so I'm reaching out to the community. Thank you all for all the help we've had so far. So happy to take any questions. Tell you about compilers? Yeah, so GCC has been approved for upstreaming now, so it should be upstream pretty soon. LLVM has been, the patches are in the upstream flow for LLVM as well. So both LLVM and GCC are very much in progress in being mainlined.
Currently, you program in Asanovic.
Say again?
What language do you use now?
What language do we use now? It's mostly C, C. I mean, those are all available. The ports are done. We're just upstreaming them. They've been used, the GCC and LLVM have been around for many years and been iterated. It's just right now we're in the process of upstreaming the ports so they'll be managed by the mainline. Yeah. Yeah, so, Linux and BSD are all up and running. A few other OSs are running other places. But yeah, there's a lot of existing code out there. The Go programming language from Google, that's being ported. Rust, I know, lots of Python, lots of stuff just works, so out of the box right now. Yep.
When will we see the equivalent of the Raspberry Pi for RISC-V?
I would say about end of next year. Yeah. Right. Yep.
How much faster are the TLB lookups than on AMD64?
So that's actually a microarchitectural question. The answer is way faster or way slower, depending on who did the implementation, right? So,
Can you repeat the question?
How much faster are the TLB lookups on RISC-V versus the AMD 64? So that's really a microarchitectural question. So if you wanted to build a core that was really good at that, you could. That's one of the big differences, right? With AMD 64, it's you wait for Intel or AMD to build you a core that works better. But if you're an application domain and you had a chip partner, you could go build something that had the most amazing TLB hierarchy ever for your application, right? So the point is that's really a microarchitecture question, not an ISA question. Yeah, and similarly when people ask me, is it lower power than an ARM core? You know, for the same performance and same design effort, yes, it would be. But it really depends on that particular project, how much implementation effort went into that goal versus other goals.
Does it have an interlocking pipeline?
Does it have an interlocking pipeline? Oh yeah, the instruction set is sequential. So the behavior of one instruction is available to the next instruction. So there are no exposed pipeline hazards. And actually, getting back to TLB, one thing we did in the privileged architecture is the way we handle TLB and page table coherence is there's actually a system fence.vm. So TLB is not exposed to the supervisor, and we can hide that behind the S fence. So basically, instead of saying, you know, flush the TLB and wait 5 cycles, you say, I write to the PTEs, and then I do an S fence. And that makes sure that the translation unit will see those updates to there, right? We want to avoid any kind of exposed pipeline hazards because we want to support a wide range of implementations. Okay, I think that's it. All right, there's one more? Oh yeah.
The HDI hypervisor interface, does it, I mean, is there any assumption on type 1 versus type 2?
Sorry, I didn't.
It seems like this hypervisor interface is fine.
Yeah, so we actually left space for a type 1 hypervisor mode. There was no interest in it, so nobody's pushed on that. There is space to do it. I would say like until about a year ago, nobody was interested in hypervisors at all because there's too much other stuff to do. All the recent interest I've had has been in type 2 hypervisors just in supervisor mode. So I think the sort of Linux KVM style, which I guess is the same as the BSD Beehive thing, I think that's where the effort and development will go. And that's kind of on the roadmap for this next year to figure that out. But that's the plan, is to focus on those. We'll keep the hypervisor mode in there, even if it's as a part of the spec. You don't have to implement it in the chips. So, yeah.
It sounds like this processor is compatible with Intel processor, right? That Intel still is sponsor?
Yeah, so Intel has been the largest industrial sponsor of RISC-V. Whether they know that or not, but they've actually, no, they're very much aware. Intel is very schizophrenic about RISC-V. So parts of Intel love it, parts of Intel are scared by it. But they've been the biggest sponsor, and they continue to be a big sponsor. So, a RISC-V.
Can you share where they're using it?
Intel is not using it to my knowledge right now, but they've been sponsoring it. One reason they like it is Intel is upset about how hard it is to find graduates who understand how processors work. A lot of other schools teach people on simulators that have little resemblance to reality. So they like RISC-V because people can see a real processor running a real stack. And so they're sponsoring it. A big part is an education mission. Give people something real that actually runs all the regular software so people really understand how systems are put together. So from that perspective, they're very favorable towards RISC-V. And they like to support it in that way because they cannot give away x86 implementations. And even if they did, nobody would have time in a 30-year PhD to understand it. So, yeah. All right. Okay.